Good afternoon, dear colleagues. My name is Alena Balalaeva. Today I want to present for your consideration the work of our team of authors, image compression research based on convolutional autoencoder. With rapid advancement of information technology and the growing volume of digital content, there is increasing need for efficient data compression methods. Classical image compression methods, JPEG, PNG, GIF, and TIFF, have their own strengths and weaknesses. For example, JPEG works well for photographs but can introduce noticeable artifacts when compressed too much, while PNG preserves high image quality but results in larger file sizes. Neural networks can offer a new approach to image compression. The main advantage being the ability to learn from large datasets, identify patterns, and extract the most important information from an image. The goal of the study is assess the effectiveness of image compression algorithms based on neural networks and compare them with traditional compression methods. One popular approach is the autoencoder, a type of neural network used in encoding and decoding data. It's commonly applied in dimensionality reduction and noise removal and consists of two main components. Encoder, which compressed the input data by identifying and keeping only the most essential features while discarding noise and irrelevant information. Decoder, which restores the original image from the compressed data as accurately. The main advantages of autoencoder include the ease of implementation and configuration, as well as adaptability to different data types. The encoder model is a complex system of functions that encodes and decodes the input data using neural networks. The model aims to find a latent representation of the data, which would minimize information loss during the image restoration process. An autoencoder can be represented as a pair of functions: encoder, decoder. The encoder performs a series of convolutional operations. After a sequence of convolutions, a latent vector is obtained. The decoder restores the image from the latent space using transposed convolutional layers. The model described outlines the functioning of the autoencoder and illustrates how the neural network encodes and restores the image through the latent space. To train the model to correctly identify image features and achieve optimal reconstruction quality, a hybrid loss function is employed. This function combines three components: SSIM loss, perceptual loss based on VGG16, and MSE loss. Hybrid loss function enables balancing between numerical precision, structural similarity, and high-level features. SSIM loss, structural similarity index loss, assesses the similarity between two images by corresponding structural characteristics such as brightness, contrast, and texture. Perceptual loss leverages intermediate features from the VGG16 neural network pre-trained on the ImageNet dataset. It measures the similarity between the true images and the predicted images at the feature map level rather than at the pixel level. To conduct the experiment, a modular software system was developed in Python comprising the following components: graphical user interface, compression module, which handles the encoding and decoding of images using the autoencoder model. Quality assessment model, which computes the key evaluation metrics, specifically PSNR and SSIM. To perform the experiments, 4 encoder configurations were developed, incorporating 3 layers, 5 layers, 7 layers, and 10 layers of convolution. The results obtained using the 3 layers encoder are presented on slide 4. The model achieved an SSIM score of 0.97. An SSIM value close to 1 indicates a high-level degree of structural similarity between the compressed image and its original. The SSIM distribution is presented in Figure 3a. The PSNR for JPEG compression is 41.11 dB, while the autoencoder achieves 27.09 dB. However, while PSNR is an important quality parameter, it doesn't always correlate with perceptual visual quality. The distribution of PSNR is illustrated in Figure 3b. The JPEG compression ratio is nearly 4 times higher than that achieved by the model. Therefore, the autoencoder currently exhibits limited compression efficiency. The compression ratio distribution is shown in Figure 3c. Visually, both images are similar to the original with no noticeable artifacts. These results indicate that while the autoencoder achieves higher quality image restoration, as indicated by SSIM, it still lags behind JPEG in terms of compression efficiency and processing speed. Next, we evaluate the performance of the 5-layer autoencoder and compare it to JPEG, slide 5. This model achieves an SSIM of 0.93. This presents a slight decrease in image quality compared to the 3-layer model. See Figure 6a. The 5-layer model also performs worse than JPEG in terms of PSNR, 25.78 VC 36.37. However, the gap between the two is narrower. A notable characteristic of the JPEG method is its ability to adjust the trade-off between the quality and compression. This means that as the SSIM decreases, the compression ratio increases, as evident from the experiment's results. The 5-layer autoencoder demonstrates a slightly better compression ratio compared to the 3-layer model, 1.11 VC while 1.18. However, the difference is minimal when compared to JPEG. The compression ratio distribution is shown in Figure 6c. The visual compression is presented in Figure 5. The images still closely resemble the original, so a slight difference in color becomes apparent. In comparison to the 3-layer model, there is a modest reduction in both SSIM and PSNR values. However, a small increase in compression ratio is observed. This indicates that the compression process performed by the autoencoder is lossy, with the compression ratio depends on the quality of the original. We now turn to performance of the 7-layer autoencoder model, slide 6, Figure 7. And SSIM is 0.85. A noticeable decline in SSAM indicates potential overfitting in this model. With an excessive number of parameters, the model may start to memorize the training data rather than generalizing from them. Despite this, the restored images maintain clear structure, especially when compared to JPEG, where image blocking becomes evident. However, the restored images show a near complete absence of green color. Figure 8AB and some finer details been to blur. Figure 8C. Based on this observation, we can conclude that for images of size 128 on 128 pixels, using a model with more than 5 convolutional layers is not advisable. Next, we examine a case of significant overfitting with the 10-layer model. Figure 9. The SSM is 0.8. Due to significant overfitting, the model generated artifacts as illustrated in Figure 10. Overall, the restored images frequently display facial features or even entire faces in areas where they should not be present. The study demonstrated that overly deep models tend to underperform in this context. The findings of this research indicate that at present neural networks are not yet able to outperform traditional compression methods, suggesting that this area requires further exploration. Neural networks can reconstruct images with adequate quality. They still fall short of compressional efficiency and computational performance offered by classical methods. This study developed an autoencoder model for image compression. The experiments demonstrated that the proposed model successfully preserves key structural features of the images, while achieved significantly lower compression ratio when compared to JPEG. The experiments determined the maximum acceptable number of convolutional layers for the model. For images of size 128 on 128 pixels, the maximum acceptable number of convolutional layers was found to be 5, with 2 or 3 layers being the most effective configuration. The analysis of the experimental data highlighted two main challenges for the neural network-based approach: a low compression ratio and high resource requirements. Optimizing the model architecture could enhance compression efficiency. Further improvements can be made through model optimization and compression. The results indicate that without addressing the computational cost, neural network-based compression methods cannot replace traditional approaches.